Okay. So welcome to the seminar, everyone. We're happy to have Davar Khoshnevisan. His research is in SPDs and particle systems. He did his PhD in Berkeley and then spent a few postdoc years in MIT and University of Washington before moving to the University of Utah, where he's now a professor. His research is very good. He has many accolades, including the Rowland-Davidson Prize. He's a fellow of the IMS and a fellow of the American Math Society. So obviously, we're very happy to have him. Please take it away, Davar.
Thank you for your kind invitation. Let me see if I can do this properly again. Here we go. It's of course a pleasure to see you all virtually, and in many cases it's been many years, so it's very nice to see you. Thanks for having me. This is based on ongoing joint work with my collaborators Kunwoo Kim, who's at POSTECH, and Carl Mueller, who's in the University of Washington. And of course, I'd like to acknowledge generous support for this and many related projects before this by the National Science Foundation. So for your convenience, I will try to maintain the form of the stochastic PD or the SPD on the top of the page. It's just so you remember what the topic is. I might fail once or twice, but hopefully it'll be done otherwise relatively consistently. The topic is the stochastic heat equation, or SHE, which is basically a heat equation in a random environment. So as you can see here, you have just an ordinary linear heat equation, which we will solve on the real line. So t is, of course, time positive, x is in the real line, is a real number. U is u of tx, as I've tried to denote here. So it's a function of space-time. And it solves this random partial differential equation with a multiplicative forcing term here, which is psi. As is frequently the most common model for the noise in such problems is space-time white noise. There are many other natural models, but this is the one that doesn't require any modeling. It's the most fundamental one there is, and that means it's a centered random Gaussian distribution. So it's not a function; it is a distribution, but it's a random Gaussian distribution in an appropriate HP space with p equals minus that negative number, and the covariance measure is point mass in time and point mass in space. So if t and x were discrete, this would be just a sequence of IID normal random variables. And this is a continuous space-time model of more or less that phenomenon, but as many of you might know, an uncountable number of such IID normal random variables can't be constructed in an appropriate space with a good integration theory. What one needs instead is this. So of course, every stochastic PD of this type would need an initial value. So this is a random initial value problem. So I will assume, at least for the purposes of this talk, that what we have is, let's say, bounded or essentially bounded measurable function. It's non-negative or non-negative almost everywhere. If it's random, it would be independent of the noise, and instead of bounded, it would be bounded in LP. So its LP norms are bounded. But let's just say it's a non-random function. And this condition here is just another way to say that, yes, it's non-negative, but it has to be strictly positive on a set of positive Lebesgue measures. So it's not zero. Okay. The only other term here I think that I have not yet defined is this, what you can call diffusion coefficient sigma. So sigma is a function from the real line to the real line, and I'm going to assume that it's non-random and that it is Lipschitz continuous. So once you assume that it's Lipschitz continuous and non-random, there's a very well-established solution theory for such an equation. Bottom line is there exists a unique solution. Unique is interpreted appropriately. That's a very natural object. We're going to assume, in addition to all this, that sigma of 0 is 0. So sigma actually vanishes at 0. Now, this is for us an important assumption. There is no maximum principle for SPDEs. I don't mean people don't know it exists. I mean people know it doesn't exist. However, there is a comparison principle, which means that if you start your SPD, this is the SPD, but instead of starting it at, say, a given U0, like I'm doing, if you started at two different initial data, U0 and B0, and keep track of the solutions, U and V, UTX and BTX, if U0 sits above V0 everywhere, then, so that means if the solution at time 0 sits above another one, then at all times they sit above one another. They never cross. So that's a maximum principle of a type. That does hold for SPDEs. It's due to my collaborator Mueller in some sense, and also Shiga at the same time. And there have been many others, Donati, Martin, Pardou, and so forth, who've discovered this in various directions. And what this condition does for us is it ensures that if you start positive, which we are because of this assumption, then the solution is always positive. Because if sigma of 0 is 0, you can easily convince yourself, if you start this equation at time 0 at 0, then it always stays at 0. That's not hard to see. I mean, the heat equation certainly maps the constants to constants. So if you start the non-random heat equation at 0, of course, it's always 0. What I'm telling you is if the sigma shuts off the noise when the solution is at 0, and that happens at time 0, then it always stays at 0. So what this says is, if you start at 0, you're always 0. Because you started above 0, you're always above 0. So this ensures positivity. So, and models of this type that satisfy equations as properties of this come up, for example, when the solution here is supposed to represent the density of a particle system. Densities are supposed to be positive. Okay, so if you have sigmas, if you have an SPD of this type with a function sigma, sigma would have to basically vanish at 0 for this to be a physical model. Maybe a slightly unexpected result. In fact, it's a quite hard result to prove. But maybe one would expect this by analogy with non-random heat equations, is that in fact, if the solution is bigger than or equal to 0 times 0, which it is, and it's positive on a set of measures 0, then it's strictly positive elsewhere at all other times, everywhere. Certainly, if you didn't have randomness, that would be true, because the solution is just convolution of the initial data of the Gaussian. So as long as you're strictly positive on a set of measures 0 times 0, at all times, you'll be strictly positive. It's true in the stochastic setting as well, but for more interesting reasons, which I can't get into, but roughly it's because of this property, that the solution to this SPDE, with or without sigma of 0 equals 0, is actually a strong Markov process. However, UTX is not a Markov process in T. UT is an infinite dimensional strong Markov process. You need to know all of UTX for every X, and then evolve time to see a Markov process. So that's been known in different settings and various contexts for a long time. For linear SPDs, certainly since 70s, and for nonlinear SPDs, I have a reference here in the 90s, but I think it predates that as well. And once you know that, once you know the Markov property, you can prove, and Mueller did, with a very nice argument, stopping time argument, that because it's bigger than or equal to 0, in fact, it's strictly positive at all times above 0, not t equals 0, because it could be 0 on a set of measures, even positive measure, but at all other times, it will be strictly positive everywhere. And please note, I'm being fussy, but the null set does not depend on where it's positive. So it's even at random t's and random x's, UTX is positive. It's really a positive random function, strictly positive random function. Now, we're going to restrict things further for reasons that I'll try to explain, this is less physical reasons maybe, but there are good motivations for this. So first of all, sigma is Lipschitz. That's a very basic assumption in the basic theory of stochastic PDEs. That just means that the Lipschitz constant is finite. So that's this thing here on the right. Lipschitz means this is finite. I think we all know that. We will additionally ask that this quantity is strictly positive. So in a way, if sigma were, I'd say, convexity properties, this would, infimum would be the same as limit as a goes to 0. So that says that the derivative of sigma at 0 is positive. Okay, it's a little more than that, but not much more. And in fact, together, these assumptions are essentially equivalent to the condition that you see here, that the graph of sigma, or maybe absolute value of sigma, lies in a cone. And the cone has two constants, L and lip, which play a role in the whole theory, actually. So sigma is, in this sense, a perturbation of a linear function, the standing assumption. Okay? So it's not just any SPDE. These are SPDEs that have non-negative solutions with diffusion coefficients that behave like a linear function in this sense. Now, what does this do? What such equations do when you simulate them? Every now and then, as time evolves, they produce pictures like this. So what you're seeing here on the x-axis is the variable x, that's the spatial variable. On the y-axis, what you see is the solution, UTX, at time t. So I've taken a snapshot of the system. If this is a density of a particle system, I've basically taken a snapshot of the particle system densities everywhere at the given time t. Now, you have to simulate this for a very wide span of x's. X lies in a real line. So you have to simulate this on a very wide span of x's over vastly large time scales. If you do, that can be expensive. But if you do, and I've done this for sigma of x being x, what you see is a picture like that every now and then. The solution is positive. So where it looks like it's 0, it's not 0. It's just that the peaks are so big that in order for MATLAB to actually accommodate the plotting of this, it forces these smaller values to look like 0. They're not 0. Mueller's theorem says they're strictly positive. What's interesting about this is that what you're seeing is very, very large peaks that are distributed over very, very narrow islands and separated by relatively wide valleys. And the language is actually borrowed from fields outside of the mathematics that use this language. So in fact, this phenomenon, which is called intermittency, people in time series know this very well, for example. This phenomenon was actually observed in climate science first, as far as I know. First people who discovered this were, I think, Batchelor and Townsend, and they announced it in the 1949 meeting or 48 meeting in WHO, World Health Organization. It was a meeting on atmospheric science. There's a lovely paper they wrote after that in the Cambridge PhilSoc, where they start the paper by saying, we really don't know why this is happening. We're just observing that this is happening in all sorts of problems of random fluids that we're seeing in this context of climate. And the bottom line is, we now know why this is happening. It's happening because everything's forced by a noise. Turn here. Something that I think we owe to Zeldovich's work in a different field in the 1980s, in this study of, in his very famous study of the distribution, large-scale distribution of galaxies. In any event, in terms of math, there has been in the past 10 years lots of papers written about the distribution of the peaks, the size of the peaks, the general local structure of the peaks. Very little is known about the islands over which these peaks sit, and even less known about the valleys, the voids, in between these peaks. And you can sort of see why so little is known. It's not so easy to actually talk about these things as mathematicians. So part of the game is to actually find out what we can prove and what we can state that actually corresponds to these pictures. Today's goal is to say a few things about the valleys, or sometimes called voids. In the context of, so if this is actually the density picture of galaxies, for example, these voids are actually called voids, and a big problem in this area, not just SPDs, but the actual area where the things really aren't SPDs, but really distribution of galaxies is voidal dynamics. So not only what these voids look like, but how do they move in time? These are important questions in that particular neck of the woods. But the question about valleys has similar meanings in other fields. And I want to say a few things about those. I've already introduced this object a lot, the parabolic Anderson model. So that's when sigma is not sitting in a cone between two lines, it's actually a line. And this particular model was invented, or was coined in a very important paper in the memoirs of the AMS by Carl Mueller and Molchanov. They wanted to solve this equation not just on R, but on higher dimensional spaces for maybe obvious reasons. The equation itself doesn't have solutions in that case, and so they discretized R, and so they solved a different SPD, which is more or less has the same flavor. It's the stochastic heat equation with multiplicative noise term, where Xi is any Gaussian noise. It could be delta mass for both. It doesn't have to be. And this is the graph Laplacian on ZD. So basically, if you formally take this to a continuum limit model, and this can be done rigorously in d equals 1, graph Laplacian in the limit becomes second derivative. And these things are taken to be point mass as their measures. And that's the SPD we're studying. So the parabolic Anderson model, in our case, is a special case of what we're talking about. Of course, this particular SPD is quite central. Here are some really important contributions that have recently arisen in a different context yet, which is to do with KPZ universality. Lots of statistical mechanics models are supposed to converge to an object called the KPZ fixed point, which you can relate to functionals of this SPD by taking the appropriate limits, or at least some of this is rigorously known, and some of this is not. I think I'm going to not say more about that. That's a huge topic in its own right. But as you can see, there are some amazing mathematicians on this list who are contributing as we speak in that direction. And for the KPZ equation, and that's actually what I've simulated here for you, for the parabolic Anderson model. So that's this SPD right here. That's what I've simulated for you. What you can sort of see is that, in fact, this equation has lots of scaling properties, or if you can't see it, I hope you'll just trust me, it's true, which suggests that, in fact, these valleys themselves look like small-scaled versions of the big picture. This is a linear equation. It has a lot, and everybody here has scaling properties. The heat operator has scaling properties. White noise has scaling properties, and therefore, so does the solution here. And so it stands to reason to think that typical valleys here, typical voidal regions, actually should look like scaled versions of the big picture every now and then on the right scale, and they do. And this suggests that there should be peaks within peaks within peaks, and that's sort of a multifractal story of a type. And that's been predicted as well in the physics literature. And we sort of proved a version of that using a device called the macroscopic Hausdorff dimension that was invented by Martin Barlow and James Taylor, actually to describe fractals in physics models where the fractals are not sort of getting more complicated as you zoom in, but rather the fractals get more complicated as you zoom out. So they're asymptotic versions or macroscopic versions of the usual notion of Hausdorff dimension and analysis of fractals that are nice. And so we actually use exactly that to describe multifractality. And so allow me to show you a theorem about that. I mean, how do you state these things as math theorems? So, well, so before we do that, let me say a few more things about what people have done in this context. Again, most of the work this is a huge literature on this topic, and so in that sense, most of the work is about the parabolic Anderson model, which is when the diffusion coefficient is linear. So there's a very, very influential paper by Kardar, Parisi, and Zhang. Parisi recently won the Nobel Prize for his work on materials physics. In this case, they actually predicted that in sigma of u equals u, that equation should play sort of a fundamental role in all sorts of statistical mechanics models. And subsequently, Kardar, in fact, even predicted using what's called the beta ansatz. He predicted the conjecture, or predicted that the moments of the solution at a fixed time and a fixed x should look like this function when the time is large. The minus sign is incorrect. I apologize. It should be a plus. I don't know if I can correct this on the fly, but let me attempt that, and we will see if that works. Can you see the difference? The minus sign. Okay. So that's the correct formula. And what I haven't written here, but it's sort of tacitly assumed, is that m here is a strictly positive number. Could be an integer, need not be. And the statement should be that in some natural sense, the most natural one would be to take logs of both sides and divide by t and let t go to infinity. Then in that sense, this equation should be asymptotically correct. This has been proved by Sha-Chen. This is true. There are earlier ideas in papers by Bertini and Cancrini as well. And there are also several papers where these are rigorous papers, but they also make semi-rigorous arguments that say if you had a moment estimate like this, then using sort of arguments that look like ergodic theory arguments, then you would expect to have lots of peaks. And I mentioned some of the math papers where this is done in the introduction, for example, as part of motivation for what they do. Okay. And even if you don't have parabolic Anderson models, so the full sigma nonlinear model as we have it, there's some work on this sort of moment estimates as well. Okay, so this is the first work toward multifractality, or first series of works toward multifractality. How do you state multifractality? Well, here's one way to try to state things. You estimate moments, so that's a concrete mathematical problem. And then you argue that if you had moment estimates of this type, you see what's really happening is that the second moment is growing vastly faster than the first moment. The third moment grows vastly faster than the fourth moment, than the second moment. As m grows, these moments grow on different scales, and it's that which can be used to build an argument of multifractality. Okay, and more recently, we actually had a full statement of multifractality, which I also do want to show you. So let capital dim denote macroscopic Hausdorff dimension. I don't want to describe this, but if precisely, but roughly speaking, if you think about the usual definition of Hausdorff dimension, what you try to do, and this is not so easy to do, but that's what Barlow and Taylor did, what you try to do is write a version of it that's defined inside out. So instead of zooming in to find a notion of dimension, you zoom out at the infinite structure of the set that you're interested in to define a notion of dimension. And that's what Barlow and Taylor did. So I think we should just accept that as a notion of dimension rather than get into the definitions, and then I can state the theorem. So it looks a little bit messy, but basically it says you look in space-time at the points t comma x, you have to rescale t so that time moves very rapidly. because this is on a very large time scale. But barring that, you look at points t comma x, where the solution is huge, is like e to the beta t. Beta is a free parameter. And what the statement says is basically the dimension of this set is 2 minus constant times beta to the 3 over 2. And so you can turn this around and then see that there are infinitely many betas, hence infinitely many lengths of peaks, all different, with different, where the points where these peaks are attained have different dimensions. So this is a sense of multifractality that can be stated rigorously for such equations. So this is something we did a few years ago. There are variations of this as well. You can fix time and just say, okay, I've taken a fixed time t equals 1. I'm just going to look at the function of space. Do I see multifractals? So that was actually our first attempt. This was conjectured by Zimmerman et al. In physics literature about 20 years ago. This was what we were trying to prove, but we couldn't prove it at the beginning of our attempts. And what we just did was fix time and do analysis. And that appeared here. And since then, people have also been able to use integral probability methods in the case where sigma of u equals u. In particular, Cheyenne Das and Parmeet Gosal. And Parmeet Gosal and Yi have Yi have proved that if you fix x, the space variable, and let t evolve, you also see multifractals. And this is quite interesting because when t evolves, this is a process with very, very long memory. So this is a serious undertaking. It isn't just some extension of known results. So in the context of values, what does this result about multifractality teach us? None of this is new stuff. I hope to get to new stuff in a moment. So think about x as your variable. T will evolve, but I'm really thinking of taking a picture of the solution as a function of x and then letting that evolve with time. That's how things move in a Markovian fashion anyway. So think about x equals 0 and look at the largest connected component of 0, where everywhere above that, you're small. Let's say you're less than epsilon. Epsilon is fixed. That component might be empty, so maybe that valley is empty. But I'm interested in the valley that straddles 0. And it has a length, so if the valley is empty, the length is 0, there's nothing to do. But the point here is that what this actually proves, and that's because of this e to a t over theta. What this actually proves is that there will be infinitely many times, t1, t2, etc., they're unbounded, random times, where the length of the valley can't grow faster than e to a constant times t. That's this e to a t over theta, basically. Okay, so here's a rigorous statement. The lim inf of log of LT over T is almost surely finite. That's a consequence of this thing. What we're interested in here for the analysis of the value, this comes from the analysis of the multifractal distribution of the peaks. What we want to know is actually how big the valleys can get. So actually the point of this talk really is to say some things about a lower bound, which is that eventually at all times, the length of the valley will be at least e to a constant times t to a third. So I would like to say a few things about what's required in the proof of a statement like this. That's actually our goal here. You can sort of see that there's a huge gap between the known upper bound and the known lower bound. It's very difficult to make conjectures on what is and isn't sharp, partly because when you look at these valleys, the valleys themselves typically tend to look like the whole picture. And so because of intermittency, what you would expect is that the low points in the valley don't look anything like the high points in the valley. And basically these methods, the way they work, they study only the low points and the high points. Whereas in some sense, you need, for a proper asymptotic description, you need to know a global description of the peaks. And that's very hard to do because of intermittency. So this is why there's a pretty big gap in this known part of this very small world. And as I've tried to mention, actually, in order to study this, you also have to sort of have some understanding of what the solution looks like over this valley. And so the soup of the solution over the valley has to have, we have to find some estimates. So that's a free byproduct of this analysis. And in fact, I think I can show you the main theorem. So suppose that the initial data is everywhere constant, or by comparison, it could be any bounded function whose infimum over the whole line is strictly positive. But let's just say it's 1. So it's at time 0, we look at u0 equals 1. For every x, u0 of x is 1, and then we evolve ut of x according to this stochastic PD. And the statement is that there are two non-random numbers. They're strictly positive and finite, lambda 1 and lambda 2, and they're not random, such that if you look at the maximum height of the solution in an interval that straddles the origin, so x equals 0 is always inside this interval. So that's telling you something about valleys that straddle the origin. If you look at the soup of the solution between minus e to constant t to a third and plus e to constant t to a third, now the soup of the solution is very small, actually. The solution is going to 0 as also e to constant t to a third. Or I should say not as, but at most as. So that's the theorem. So first of all, that means that if t is large, there is a valley that straddles the origin because the soup near the origin goes below epsilon for your favorite epsilon. And the valley is at least as big as the interval minus e to a constant t to a third to plus e to a constant t to a third. And that was what I claimed here. But the length of the valley eventually is bigger than e to constant t to a third. So that's the statement. And as a free byproduct, we get also an estimate on the maximum of the solution over at least the bulk of the valley. There are, in fact, versions of this that are slightly stronger. So I'm sorry, the way I'm presenting it, it seems like these are totally different theorems. Actually, theorem 2 is used to prove theorem 1. But nonetheless, it's sort of it stands on its own as well. That says if instead of u0 equals 1, so if at time 0, you don't start from 1, but you start with something that has Gaussian tails, sub-Gaussian tails. So one of the things that's known is if you start at initial distribution with tails that are very quickly going to 0, then the solution to this SPD is almost surely bounded, uniformly bounded at all times. That's not obvious because it's a function indexed by the real line. So, but it is true that if u0 dies sufficiently rapidly at infinity and minus infinity, the solution is bounded. So the soup is finite. And what this is telling you is that the soup actually goes to 0, not faster than e to some other constant times t to the third. This should say lambda 3. I apologize. It does not, but it should. So and again, I apologize again that the theorem 2 is presented as if it's a theorem that stands on its own, and maybe it does or maybe it doesn't. It's actually the first step of the proof of theorem, which is really our attempt to give bounds on the length of the values. So theorem 2 gets us a little bit closer to perhaps where we're comfortable, where there are mathematical tools. In fact, there are sort of martingale arguments that can be used as part of the proof of theorem 2, and I'll show you what the martingale really is in a moment, and why we could expect theorem 2 pretty quickly. And then what I hope to do is spend a few minutes, if I can, and if I have enough time, to show you. So there's a big difference here. You see here, the initial data goes to 0. Here it does not. How do you deduce one from the other? So this is about theorem 2, which is where the initial data has sub-Gaussian tails. Let's think of initial data as having compact support, in fact. So it's known, as I said, that the solution has a bounded supremum. It also is actually integral. Please remember also that the solution is positive. So because it's integrable, its integral is actually the L1 norm. And the argument, the critical observation in this setting is that the L1 norm, which is a stochastic process indexed by time, is a continuous process indexed by time, is actually a continuous martingale. Now, this has been known in the context of discrete particle systems for a very long time. I think it goes back to the 1981 paper of Spitzer. This thing is called total mass. So if you integrate the density of a particle system, total mass is typically a martingale indexed by time. And so it is in this continuous setting as well. And it's easy to see why. If you solve this using the Hummel's principle, so let Ptx denote the density of Brownian motion at time t at space x. Okay, that's Brownian motion because of this operator here. And just use the Hummel's principle here, or variation of constants. What you get is an explicit integral equation that the solution solves. In other words, what this really means is this integral equation. This is space-time white noise, so this is a Ito-type Walsh stochastic integral. And star means convolution. So you convolute. So the convolution of the the convolution of the Gaussian with the initial data just solves the linear heat equation. That's just that. And then you perturb off of that to account for the forcing, and you get a stochastic convolution with a noise. U appears on both sides of this equation. There's the solution, there's the solution. So this is an integral equation. It's not an identity. But the statement is this has a unique solution. That's a rather old, very well-known theorem. So now what you do is you integrate both sides. Please remember, things are positive, so the L1 norm is just the integral. So I can integrate dx, both sides. If you integrate the convolution, you see the integral of pt is 1, so you just get the integral of u0. u0 is positive, so that's the L1 norm. If you integrate the stochastic integral, there is this thing called the stochastic Fourier. That's not surprising. These things are linear operators of a sort, so the integrals exchange. If you integrate the heat kernel, you get 1. So once you integrate that, you end up with a stochastic integral of this type. Now, I want to remind you or tell you if you don't happen to know this, these Walsh-Ito integrals are integrals of two parameters, ds and dy. In dy, they act like a continuous version of inner product. So if instead of x being in R, x were in a finite set, the integral dy would just be a sum of a bunch of independent Brownian motions. It's the integral ds that's an Ito integral. That's what makes this a martingale. Okay? It's basically an integral of a bunch of Brownian motions from 0 to t. So this is a continuous martingale. What makes it a little bit complicated to analyze is that the quadratic variation of the martingale itself has the solution itself in it. It's not just a function of the L1 norm. So it's not closable in the language of physicists. But it is, at least we have some object, a martingale here. And what you can prove about this martingale, and we did this a few years ago with Lachan, who's in Auburn, Mike Cranston, who's in Irvine, and with Kunwoo Kim, who's in POSTECH, is that in fact, if the initial data is sub-Gaussian, then this martingale will go to 0 at most as fast as e to the minus constant times t to the third. And so if I go back to the theorem 2, the statement was that the soup goes at most like e to the minus t to the third. And what I'm telling you is that the martingale already goes e to the minus t to the third. And the martingale is the L1 norm. So maybe it's not so surprising that the soup does too. And the way you prove this is you try to get moment estimates for martingales. Of course, the natural way to do it is using Burkholder-Davis-Gundy. The effective way of doing that is to get moments that are moment numbers bigger than or equal to 2. That's not going to work because of intermittency. The moments grow too fast. What you really need are small moments. So we estimate the half moment. We estimate this one. And it's a martingale, you use Ito formula. So you write an expression for the half moment, and you can't close the expression. In other words, you don't get an identity that represents this half moment in terms of the integrals of itself. So then you perform some calculations and estimates, best you can, to get an inequality. And what you end with is a differential inequality that says, okay, this function f of t, its derivative is less than some complicated function of f. You can solve that differential inequality, and that says that any solution to that differential inequality grows at most like e to the minus a fixed constant times t to a third. Therefore, so does this one. And that's the bound. From expectation to almost sure is easy, because if you take a square root of a martingale, you get a super martingale. So you have a maximal inequality. Because you have expected value of a super martingale less than this, expected value of the running supremum is also less than this, maybe multiplied by some other constant, Dub's inequality. Once you have a maximal inequality, you use Borel-Cantelli lemma, and you get almost sure. So this is the first part of the proof. Again, pretty well known, but it is very suggestive that if the L1 norm is small, maybe the L infinity norm is also small.
Davar, can I ask the question?
Of course.
Do you mind going back to the previous slide? So I'm trying to understand this martingale argument, which is kind of new to me. That so when you integrate out x, it becomes a martingale, but it wouldn't be a martingale if x was just like a fixed x, right?
That's right. It's not a martingale.
Right.
Because
Okay.
because if you look at this expression here, there's a t here.
Yeah.
It's really not a martingale.
Oh, I see. Because when you integrate that out, oh, okay.
Yeah. I mean, it has some properties of martingales, right? Because you can view this. I mean, if you're, for example, interested in the second moment of this, you can pretend this is T1 and this is T2. It's a martingale in T2. You use martingale facts to estimate the second moment. But if you're actually interested in dynamical properties, how does this evolve as T evolves? You can't ignore this T here. It's really there.
Yeah. Okay, thanks.
And in fact, this is how Spitzer understood that one way to study certain types of such systems is to remove that extra T by looking not at the solution, but at the total mass of the solution. But of course, our job is not done. We still have to relate the martingale to the actual process. So this is the integral of the process. We want the soup of the process. So then the way you do that is you prove this proposition. It has all sorts of parameters in it. That's not so important. The point is, what you really want to prove is, well, you know that the L1 norm is e to minus constant times t to a third. So what you really want to prove is that the L infinity norm does not exceed the L1 norm significantly. Not faster than e to the minus t to a third. And so any polynomial rate would work. And so here is a range of polynomial rates that work. You prove that by very large time n, the infinity norm might get bigger than the L1 norm, but the probability that it gets significantly bigger is extraordinarily small. And I just want to sort of say something about why this is true. This is kind of a tricky result. It's the coarse graining argument. So you don't try to work on a very large time interval right away because there's no controlling this object, as I understand things. So what you do is you actually split this interval 0 to n into tiny, tiny steps, many of them. And then you work on each sub-interval that's very small and paste them together using the fact that the solution is a strong Markov process. In this case, Markov process. And the argument goes like this. On a very, very small time interval, so you start from, say, time 0 and you move to time epsilon, the process is continuous. So the only way that the sup norm is much bigger over that interval, is much bigger than the L1 norm, is either the L1 norm became really small somewhere in that interval, or you had a huge peak. But you're not going to have a very huge peak because over a short time interval, this thing behaves like just a non-random heat equation. This is signal, this is noise. Signal over short times wins. And what that means is, over a very short time period, it feels like a non-random heat equation with high probability. And one of the properties of the heat equation is even if at the left endpoint of the time interval, you had a huge peak, the heat equation brings down this peak very quickly. Heat operator mollifies things. It's integration against the Gaussian. Very quickly, it washes out the peak. So the probability that even if you start at a high peak at the left endpoint of the time interval, you end somewhere to, let's say, on the right of the interval with a big peak, the probability is very small. So the only other thing that could damage you and make this be false is if the L1 norm became all of a sudden really small. But that can't happen because the L1 norm is a martingale. It doesn't like to move that quickly. And so that's actually how the argument works. And so what you end up saying is, in order for you from time to 0 to time n to go from, let's say, 1 to some huge number n to the beta, lots of these small steps have to be such that you grow peaks over these small steps. But in any one of them, the conditional on all the other ones, the probability that you grow a peak is extraordinarily small. And so you can paste them together to see, therefore, the probability that enough of them work to build to a peak of this type. That probability is really small. That's the flavor of the argument.
Right, Davar, you have maybe like 5 more minutes.
Perfect.
Okay.
So the only other thing that remains is actually the original theorem. How does one prove that? So what I basically tried to outline is if the initial data dies very fast, decays very fast, then in fact a much stronger statement is true. The entire real line is a valley and the solution is very small. But of course, we're interested in the case where the valley grows and we want to know how fast, and the answer is this fast in the subscript of the soup. So how do you prove this? Well, if sigma were a linear function, you would use superimposition. You take your initial data, which is just 1, and you'd say, okay, I can write that as something that's 1 on a huge interval, 0 off of that, plus the complement, something that's 0 on a huge interval, 1 off of that. It's a linear stochastic PD, that's when sigma of u equals u. So the solutions add, just superposition of solutions. The one that's 1 on a huge interval is exactly this thing here. You're in this setting, so everything's small everywhere, no problem. It's the other one that can hurt you, and you can sort of show that the other one, you start 0 on a huge interval and then 1 outside this huge interval. How can you, inside the interval where at time 0 you're 0, how can you start building mass? Well, heat has to see the noise from infinitely far away very quickly, and it's not going to do that. That's the argument. The problem with this attempt actually is multifold, but one of them is that sigma is not linear. So it turns out that there's a version of this that can be fixed, and I'm going to do this a little bit quickly this is sort of a nice idea, I think. If you split the initial data as a sum of two datas, can you say that the solution is the sum of the two solutions? And of course, the answer is no in general, but you can sort of change things such that the answer is yes. And the way you do this is you observe that the solution to this SPD can be written this way. You just multiply and divide by UTX. Use positive, you can do this. That's certainly true. But now I would like to invite you to look at this term, sigma of u over u times space-time white noise, and view that as a noise. Now you have a linear equation with that noise. That noise depends on you, I understand that, but that's a noise. And that noise is what's called a martingale measure as well. It's not Gaussian, but it has some of the properties that space-time white noise has. And it has what's called a quadratic variation measure or a dominating measure. And its dominating measure is bounded by two deterministic constants times t, kind of like what space-time white noise does, except instead of equality, you have inequalities. So because of this, you can actually build a theory of SPDs for such noises. So there's my noise. That's the noise that depends on you, the solution to the other SPD. And now you say, okay, so I've solved that SPD. Now I want to look at more SPDs. I build this new noise and look at a linear heat equation. This is what I call parabolic Anderson model, except the solution, the noise is not Gaussian. The noise depends on the old solution. There's a solution theory for this, which looks just like the other SPDs, except this is not Gaussian. And that solution theory says that this has actually a unique solution. We just saw u solves this equation if you start from u0. That's just this statement that you can multiply and divide by u. So u is the only solution to this. When you start from u0, you only have one solution. But now you see u0 equals v0 plus w0. So now you solve this SPD, which is linear, with this noise from v0 and from w0, and you can now add. I hope that makes sense. In other words, these nonlinear SPDs do have a super solution principle, but not in terms of the SPD itself, rather about a more complicated SPD that's forced by a more general martingale measure object. Now, these SPDs in general are hopeless, except ours have this very special quadratic variation property. And so what that means is because of Burkholder-Davis-Gundy, anything you want to prove that only requires moments of the solution feels like the old SPD. They just need inequalities. So that's some hope. What we want to do doesn't just require moments. It also requires Markov property. The solution to this SPD is not Markov. But there's also a workaround for that. I want to show you my happy face before we end, but I won't be able to tell you what the workaround is. I think I am out of time, so I think this is a good place for me to end.
All right, thank you, Davar.
Thanks.
Questions? I have a, oh, go ahead, Andrew.
Yes, I was wondering whether there's any hope of describing the process of peaks by some sort of, I don't know, Poisson process, point process. I mean, I presume you don't know enough about how far apart they are to do that yet.
Well, we know some things about how far apart they are, and that was the multifractal description. So in the case where sigma of u is u, if you look at very, very tall peaks, so of course you have to quantify them, but we sort of know how to do that. Okay. And if you look at peaks that are well separated, and we know what that means, again, based on this multifractal formalism, then in fact, you can take limits as the peaks get larger over larger time periods. You will see a Poisson point process. This is true. But of course, ideally, what one would really like is not to describe peaks that are far apart, but all peaks. And then one runs into the sorts of problems that I think you're anticipating in, which is we really don't know a lot about the local distribution of peaks. Well, the reason we know some things about global distribution of peaks, it's not that hard to explain actually, is if you take, let's say you fix a time point and you look at the solution of 2 points that are very well separated. So allow me to go back to the Duhamel principle, because that's actually how I think of these stochastic PDEs. Here it is. So look at the solution to your SPDE for 2 different x points. You can do this for many x points, but 2 is good enough. And let's say u0 is 0. So you have x1 and x2, and you have 2 stochastic integrals for 2 different x's. And let's imagine x1 and x2 are extremely far apart. Okay. So what does the solution at x1 and x2 look like compared to one another? Well, the heat kernel, you see, the heat kernel here is very sharply, especially if t is small. So let's say t is small for the time being. Everything's relative anyway. So in a way, space large, t small, they aren't that different from one another. So imagine if t is small. If t is small, pt minus s is less than t. This looks like point mass. So this really, it's true that it's an integral in the y variable over the real line, but it really doesn't feel y variables that are very far from x. So we know how far, square root of t. So in other words, if you would expect that if x1 and x2 are much more far apart than square root of t from one another, then utx1 and utx2 should be not independent, but very close to independent. And that can actually be made quantitative.
Okay.
And it's that which allows one to prove Poisson point process limits, as long as we don't let peaks to become too close to one another. Once they become close to one another, the very local structure of the distribution of peaks is not deterministic. It's not given by this. It's truly random and very poorly understood, actually, particularly at modest, say, t equals 1. But I think there should be a way to get a Poisson point process with a very interesting structure for all peaks. We just don't know how to do it.
May I have another question?
Yeah, go ahead, Andre.
You started with Xi, which is somehow like collection of independent random variables. And at the end of your talk, you approach to problem where they can maybe in some way depend. But if you just initially assume that Xi are dependent, they have some covariance structure, whatever, is something known about that? Or problem probably because of some smoothness, does it make even sense? So can you please comment on that?
Right, so that's actually an extremely good question. If I had to give one answer, it would be that we don't know anything. And the reason we don't know anything is that if Xi is a general Gaussian random distribution, we don't know how to define this integral. But there are many, many examples where we do know how to define this integral. For example, if it's white in time, but has correlations in space, that can be done. And I think Walsh did that, and many others, Zapchik, many others have done that, Krylov-Rozovsky for sure. But if it's really not white noise in either time or space, then the definition of this integral becomes a problem itself. Now, when sigma of u is u, then formally, just view this as a PDE, if you will. So of course, Xi is not really a function, but nevertheless, if sigma of u equals u, one way to solve this, especially probabilistically, is through the Feynman-Katz formula. So in that case, lots of papers have been written in the case that you're interested in, where Xi is as general correlation function structure. For the space-time white noise, the Feynman-Katz formula actually blows up. So there is no Feynman-Katz formula. But sometimes there are, and when there are, then this sort of thing, in the case where sigma of u is u, can be analyzed. There are other attempts. If sigma of u equals u, this is u times a noise. So this is a multiplication of one random function with a random distribution. You can imagine, you can view this as a as an operation in the sense of Medievran calculus in Gauss space. So then you can sort of take out the infinity in the chaos expansion. And so if you interpret this product not as a real product, but as a Wick product, then also there's a large literature that can be used to address your question. If you write this as a Wick product, sigma of u is u, you can expand the solution in terms of linear chaos type objects, in terms of Hermite type polynomials. And so it becomes a question about random Gaussian series. This has also been a very fruitful undertaking in that direction.